So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kinda bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't all that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly, so the chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
Hello, everybody. Welcome to this wonderful streaming. We are here with Ira Thorpe, and my name is Nicholas Lira from ALMA Observatory. Ira is an astrophysicist at the NASA Goddard Space Flight Center outside of Washington, D.C. He's the lead scientist at NASA for the Laser Interferometer Space Antenna LISA mission, a joint effort of the European Space Agency and NASA to develop the first space-based observatory for gravitational waves. When this mission will be completed, LISA will detect ripples in the fabric of space-time caused by distant astrophysical cataclysms such as collisions of massive black holes. Did I say it right, Ira?
Yes. Yes, that all sounds good.
Yes?
Yes.
Cool, cool. Also, he has been working on LISA-related topics for nearly 20 years, including laboratory work, prototyping key technologies, participation in science operation of ESA and NASA, technology demonstration MISA for LISA Pathfinder, and development of data analysis tools for simulated LISA data. He lives in Maryland, suburbs of Washington, with his wife and 3 children, and enjoys cycling, running, and cooking when he's not doing physics. Welcome, right. Ira. Thank you to join us today. How are you?
I'm great. Thank you so much for having me.
Excellent, excellent. So today we are celebrating the Black Hole Week. This is an event that NASA launched a couple of years ago when EHT first released the first image of a black hole. We're celebrating last weekend. We were celebrating 2 years since this first image, and we're very happy to join this year in the celebration with NASA. And so first of all, please, Ira, can you explain, maybe everybody knows what a black hole is?
Sure. So, I hope most people saw the little intro video, which was done by some of my colleagues at NASA. and the little cute cartoon character describing the black hole. And I think that does a really nice job. And you can also see an image behind me of this is not an actual image. It's a beautiful artist rendition of a black hole, but it's basically a region in space which is sort of separated from the rest of space because the gravity is so extreme, right? And so it's really this concentration of gravity which arises from some sort of concentration in mass. And there's different ways that they can form. The most common way that we know of that they form is for certain kinds of stars. When they finish their normal life cycles, they will collapse into a black hole that's a few times, maybe a few tens of times the mass of our sun. But all that mass is concentrated in a much smaller area, and as a result, the gravity is much stronger. And as a result, the gravity being stronger, if you get close enough to them, even light can't escape, and so they appear black.
Excellent, excellent. So how does this, maybe we can start by explaining what is this event horizon limit and how does this affect where you're absorbed or not by the black hole?
Right, so there's sort of two main pieces to a black hole. And probably the most important one, at least for somebody like myself who's interested in trying to detect and observe black holes, is this piece you call the event horizon. And it's really, as the name horizon indicates, it's kind of a boundary, and it's the boundary between inside and outside of the black hole. And what it really means is it's the point at which if you go across that boundary, even moving at light speed, you can no longer move away from the black hole. One way to think about it is it's a little bit like being in a river that's going over a waterfall, and the speed is sort of picking up as you're going over the waterfall. And there's some point at which no matter how fast you could swim or drive your boat, you're not going to escape that plunge down into the down to the waterfall. That'd be the edge. And that's kind of what the event horizon is like. But it happens in 3 dimensions, and so it looks like a sphere or some sort of sphere type object. And yeah, the image that you're showing here, this is this famous image from the Event Horizon Telescope, where what we're really seeing is sort of the shadow that's produced by that event horizon on a background of what we call an accretion disk. So it's a bunch of hot gas. It's the artist image behind me. This is the real thing in a similar kind of color pattern. And you're seeing that central kind of hole in the donut is really coming from the shadow of the black hole.
So the shadow is the black part is the event horizon limit, or is the event horizon smaller? I believe it's smaller.
Yeah, the event horizon is a little bit smaller. So because the event horizon itself is actually the point where the light would plunge into the black hole. But if you move a little bit farther away from the event horizon and you have light passing by it, the light gets bent. And actually, this happens with all kinds of massive objects. So actually, really famously, the bending of light by our own sun, which is nowhere near as compact as a black hole, was one of the first indications that Einstein's theory of general relativity was correct. Right? There's this famous experiment done during a solar eclipse where they could observe motion or apparent motion of stars caused by the gravity of the sun. So that same kind of thing happens around a black hole, except because the black hole's gravity is so much more concentrated, you can get much more extreme bending of light. And the result of that is if you stick this black hole in that image that you were showing in front of sort of a screen where there's hot gas, that's what the accretion disk is, you can get all kinds of interesting effects coming from the fact the light is being bent around. And so yes, you're right. You basically the size of the shadow that you see is a little bit bigger than the size of the event horizon, and exactly how much bigger it is depends in some detail on all the arrangements of where is the gas and how bright is it, and what angle are we looking at, and all those kinds of things. And the scientists in the Event Horizon collaboration, which I'm personally not a part of, went through a lot of effort to try to first of all make these images and also sort of model what these images mean. What kind of exactly where is the black hole, what's its orientation, how much is it spinning, what's its mass, all that kind of information. So it's not just an image, right? The image is what the public likes to focus on. It's really a model of the system that we're looking at that has all kinds of tells us about the astrophysics of what's going on there.
Excellent. Thank you very much. So here.
Yeah.
Could you please tell us a little more about how NASA research and what is your research about black holes? Because EHT is not that NASA things, but we
sure.
published like yesterday some image with multi-telescope, and for example, there were a Chandra image. So I believe you do some pretty nice things with the black holes too.
Yeah. So, well, let me talk a little bit about just sort of NASA in general, what we do, and then I can talk more specifically about what I do. So, at NASA, of course, we're interested in studying all parts of the universe, and in particular, there's a group of NASA scientists that are focused on both ourselves trying to understand the universe, but really trying to provide facilities and provide data that the entire scientific public across the world, the professional scientists, but also the interested public scientists can access our data from our instruments and study whatever they'd like to study, including black holes. So certainly black holes are a part of that, and we study them with any kind of instrument we can get at. So you mentioned Hubble Space Telescope, which is quite famous. And any of our other space assets that we can use to look at black holes. One of the important parts is the ability to cover different parts of the electromagnetic spectrum, right? So light comes in different forms. You can have the light that we see with our eyes, visible light. You can have infrared light. You can have X-ray light, gamma ray light, all these different types. And one of the key things about being able to go to space is it helps us access parts of the electromagnetic spectrum that are hard to get to from Earth. So particularly some of the really high energies, some of the gamma rays and UV and X-ray, you need to go to space to see these things. And also some of the infrared, some of the low frequency light, you also need to go to space to see those as well. So, and then combining with instruments on the ground that are in that optical band and other bands, and also radio, we can really get a complete picture of what's going on with the black hole system. So here's an excellent image. Again, this is from mostly from the EHT collaboration, although I think the images in the top right there are actually coming from Chandra, NASA satellite. There's also NuSTAR, a NASA satellite there, Fermi, a NASA gamma ray satellite. But just for people who haven't seen this yet, if you look and again, it's not an image I personally worked on, but if you can see that familiar black hole donut at the very bottom there. And what it's showing is that's the that same picture we were looking at, really all the way down at the scale of the black hole. And then they're expanding in many orders of magnitude, many factors of 10 in scale, and showing how that black hole, basically starts to launch this jet. And then they're seeing this jet in these different kinds of light on many different scales, way out in terms of hundreds of light years, or even it looks like almost thousands of light years by the time you get to the gamma ray image. And so this is an example of what we call multi-wavelength astronomy, where you use all the different wavelengths you can get your hands on and all the different facilities you can get your hands on to try to figure out what's going on with a particular astrophysical system. And so this is an excellent example of the power of that kind of technique.
Excellent. Yeah, I believe this is all the observations are at the same time by 2017, when the first image of the black hole was actually, the data was taken. It was published and released in 2019, but because of how hard it is to analyze the data and make the image, it took almost 2 years. No?
Yeah. So as you might imagine, once you have all these different facilities, many of which are have other purposes as well, right? So it's not just black holes that we want to look at with all these different kinds of spacecraft and ground-based observatories. There's all kinds of things we need to look at. So it's a challenge to schedule these things to make sure, if you really want to look at the same object at the same time, how do you get dozens of observatories that are controlled by different countries and different institutions and such to all go look at the same spot of the sky at the same time? And so yeah, it's a big organizational challenge to make those kinds of observations.
Okay, one question I think a lot of people might have is, why, if anything, can't get out of the black hole? There are jets. How many?
Yeah. So right. So you don't get out of the event horizon, right? So if we're talking about that boundary between inside and outside the black hole, nothing comes out of that. including the jets. The jets form, well, we don't know exactly how they form, and this is part of the reason why we want to make those kinds of images that we were just looking at. Is, again, not just to have a nice image of a jet, but to then compare that image with particular models of how these jets form, which might make different predictions. But basically, as matter is falling into the black hole, it tends to always have some amount of angular momentum, right? It's just it's not falling directly towards the black hole in a straight line. It's always coming a little bit at some side. And so the black hole tends to pull it towards it, and it starts to rotate. And as it gets closer into the black hole, that rotation increases and increases. Also, the matter starts to pile up. And so as the matter starts to run into each other, you get this very hot accretion disk. Again, that's kind of the image over my shoulder here. And then that momentum can sometimes be transferred into this structure along that spin axis of all that spinning. Both the spin of the black hole itself is spinning, plus the disk itself is spinning, and you can get these jets of very high energy material and also particles and light all coming out in that direction. And that's what we see this evidence of. But yeah, trying to understand where these all come from. We understand the basics, but the details of how the jets are put together is still something that's being researched.
Excellent. I'm just going to recap for people who are joining a little late. So we just explained that a black hole is like a singularity in space-time, that because of this big mass, the gravity is almost infinite and nothing can get out of this limit called the event horizon. Is that right?
That's right.
And then we talked that we are doing a lot of observations, not only with the HT telescope, but also with other NASA, for example, Chandra, NuSTAR, or other space-based telescope to be able to see on other wavelengths the same object and have more information about them. And also, these jets that we don't know how they come, but they are pretty big actually. They are thousands of light years away from the black hole because of this high energy they have. We don't really know how they form, but they form outside the black hole, like outside the event horizon.
That's right.
And so, but now, okay, we can observe on different wavelengths, but you are working on observing on a different kind of light? No, not light. Different kind of
not even light. So right. So this is a little bit more what I personally work on. So you take that analogy I just talked about of if we look with a bunch of different kinds of light, we use radio telescopes and X-ray telescopes and infrared and optical, and we go all together to try to look at the same thing to get a full picture, a kind of hyperspectral picture of what's going on. Well, we could do even better than that if we looked at something that wasn't light. And of course, some people might be familiar with particle astrophysics, which is another channel of information that we can get. But I work on this thing called gravitational waves, and the idea there is that there's actually a whole other spectrum that's not electromagnetic radiation, not light. It's actually gravitational radiation. Yeah, here's a great picture of what a gravitational wave detector on the ground looks like. This is one of the two LIGO, or Laser Interferometric Gravitational Wave Observatory detectors in Washington State in the US. There's a second one in Louisiana. There's one in Europe called Virgo, one in Japan called Kagra, a couple others under development, various places in the world. And what's happening here is we're actually trying to pick up ripples in space-time. So when you have not so much an isolated black hole, but if you have a pair of black holes crashing into one another, they can actually make a vibration in space-time itself. And that those waves can carry across the universe, and they can come across our detectors, and they actually cause a little bit of very, very small sort of stretching and compressing of our detectors, which running in those tubes you saw in that picture are lasers. So there's basically lasers going back and forth in each of those tubes. They're about 4 kilometers long, and they change the distance of those tubes by about apart in 10 to the minus 18 meters. So tiny, tiny little fraction of a length. But the instrument's sufficiently sensitive to pick that up, and you can see these ripples in space-time. And this instrument and its twin in Louisiana made the first detection of a gravitational wave from a merger of two black holes back in 2015. And that was sort of the first time we'd looked at black holes or anything with something other than light. We use gravitational waves to do it. And now, at NASA, and also with being led with our partner agency, European Space Agency in Europe, we're looking to build a space version of this. So the idea is to take this thing, which is a few kilometers long, and scale it up to be a few million kilometers long, and we can look for really big black holes crashing into one another in the distant universe. So you might imagine, we know that there are massive black holes in the centers of galaxies. For example, in our own galaxy, there's a black hole about 4 million times the mass of our sun. We know that they're in most of the galaxies we look at seem to have a black hole in them. We also know that galaxies like our own formed from the merger of a bunch of small galaxies over the history of the universe. And so we think that when these galaxies merge, the black holes at their centers will also merge, at least some of the time. And that'll produce a very strong gravitational wave signal that we can go look for with this instrument we call LISA, or Laser Interferometer Space Antenna. And that's what I spend all my time working on, is developing that mission, again, along with a team across the world in both Europe and in the US.
Do you have a launch date approximately? Year?
Yeah, so we're expecting, so it's a European Space Agency led program, and the launch date is in the sort of early to mid 2030s. And so we're in the early part of the formulation. It takes a long time to do space missions. You have to, one of the reasons is that, unlike the way this instrument was built, I mean, this instrument took something like 4 decades between the initial concepts to making the first detection. So you have to have a lot of persistence to do these things. But one of the differences with an instrument on the ground is that you can sort of build the facility, and then you can continually upgrade the instrumentation, and you can continue to work on it as you understand it better and improve it. In space, you have to put it all together and then launch it on a rocket, and it has to survive that rocket launch and then operate. And so you need to do all of that kind of preparatory and practice work ahead of time on prototypes, and the thing that you fly, sort of has to be perfect. And so that takes time. As I also mentioned in the little intro, there was a technology demonstrator mission called LISA Pathfinder, which again was a European Space Agency lead with a NASA contribution. I was one of the NASA scientists on that as well. And this did fly, and it demonstrated some of the key technologies that we'll use on LISA. So the technology is fairly ready to go. We just need to go through the difficult process of finalizing the design and building everything.
So this discovery of gravitational waves was deserved the Nobel Prize in 2017, right? For Weiss, Barish, and Kipton, no? And
that's right.
So what are is there only black hole mergers that produce these gravitational waves, or is that the only thing that produce big enough events so we can detect them?
Yeah, that's a great question. There's many things that could potentially produce gravitational waves which we could detect. They generally involve compact objects. So black holes are kind of the most compact object, but there's other objects like neutron stars, which are almost as strong a gravity as black hole. And then a white dwarf, which is another kind of compact object. It's actually what our sun will likely evolve into. And those types of objects can also produce gravitational waves. The key with gravitational waves is that the isolated objects, an object by itself, generally won't produce a gravitational wave. It needs to be accelerating, and the best way to do that is to put it in a binary. So if you have a pair of these objects, then you can produce gravitational waves. The good thing about that is that many objects in the universe exist in binaries. It's very common. In fact, our own sun is kind of strange in the fact that it's by itself. Typically these binary stars will often evolve into systems of binary compact objects or supermassive compact objects, and then you can see the gravitational waves. And of course, the really exciting thing, those are all the things we know about, right? And if you kind of look back in history, I talked about how when we look at these different kinds of light. Well, the first time we looked at gamma rays, we saw things called gamma ray bursts that we didn't expect to see. Nobody was building a gamma ray detector to go see gamma ray bursts. They were building a gamma ray detector to do other things, and all of a sudden they see these bursts, and they say, well, whoa, what was that? And it launches a whole new area of science, and it allows us to sort of understand things. So for me, the most exciting thing about doing gravitational wave science, whether it's on the ground or in space, is that there could be a signal out there that we just don't expect. And I would love for there to be the ground-based detectors, or eventually the space-based detectors, have a persistent signal. We keep seeing these things pop up and we just don't know what they are. And we have to go back and check, are we sure they're not coming for the instrument? Yes, we're sure they're not coming. We see them in multiple instruments. We see them in different places on the sky, all that kind of stuff. And then the theory community has to go figure out what in the heck is making these things. And that's the way we really advance science. It's not so much by answering questions, right? Answering questions is nice, but it's even better to ask questions. And going and doing a new kind of observation is a great way to ask questions.
Excellent, excellent. I'm going to pick some questions from the public now.
For sure.
So Nuno is asking over Facebook, what is it possible that matter, antimatter, and microscopic black holes are created little after the Big Bang, and that microscopic black holes absorb the antimatter? Well, that is...
Yeah, well, I caught parts of that, right? So I heard about matter, antimatter. So for people that don't know, antimatter is basically like normal matter, except all the charges are reversed. And then also about microscopic black holes. So, and the Big Bang. So it's in principle, it's possible that all of those things were likely produced in the Big Bang, both the matter and antimatter. And for some reason, we're not entirely sure of. There seemed to be a little bit more regular matter than antimatter. And as we know, matter and antimatter will annihilate when they collide with one another. And so what was left over was just that excess little bit of matter. And that's what we call a symmetry breaking that, there's probably some clue there as to why that is, but I'm not enough of a particle physicist, and I'm not sure people really understand why it is that we have just matter and not an equal proportion of matter and antimatter. As far as the small black holes, they probably were produced in the Big Bang and in subsequent early parts of the universe. We don't know the details about exactly how many and how big they were. It's possible that there still could be some of those around, and they could be contributing to things like the dark matter. Although, if you go and you look in great detail about how many of them there would have to be, and where they would have to be, and what are the kind of signals they might produce, it doesn't look very, very likely. The other thing about the really small black holes, people may have heard about black hole evaporation, which is this very strange effect that was made famous by Stephen Hawking. And basically, you can get these quantum mechanic effect that causes the black holes to evaporate. They actually shrink, and energy is emitted. And it's a bit complex to try to explain why this happens. But for one of the features of this is that it happens much more strongly for small black holes. So a really, truly microscopic black hole actually evaporates pretty quickly, whereas a large one, like we would, like all the ones we know about, basically, the evaporation effect is so slow as to be not important for the age of the universe.
Excellent, excellent. We have another question from the public. I will ask you, but I might compliment it after because it has more to do with ARM, I think. But do you know how close is the EHT team to imagine the black hole at Sagittarius A star? This is from Zani, also our Facebook.
Well, so I as I said, I'm not a member of the EHT collaboration, so I can tell you what I've heard from other members. But if you are, maybe it's better, Nicolas, for you to answer.
Go, and I can try to compliment.
You're right. So from what I understand, one of the challenges with so what are the differences between the M87 black hole and the Sag A star, the black hole at the center of our galaxy? Well, the one at our galaxy, first of all, is closer, but it's also smaller in terms of its physical size. And if you work out the math in terms of the angular size, that is how big it would appear on the sky, they're kind of similar. And so it's certainly well within EHT's capability to image the Sag A star black hole. But one of the other differences about it being smaller is that all the dynamics happen faster. That's a feature just in general. Big things move slow, fast things, small things go faster. And like this accretion disk, again, like this image that I have behind me, there's an accretion, some amount of accretion and radio emissions around Sagittarius A star, and it changes on a time scale that's faster than the one that changes in M87, and so it's a little bit more difficult for the EHT data analysis because they're kind of looking at a movie instead of looking at an image. So they have to not only reconstruct what does the image look like, but they have to reconstruct that image as a function of time. So it takes more observations and takes more data analysis. So that's my understanding as a non-member about what the challenge is of doing Sagittarius A star as opposed to M87.
Yeah, what I know is more or less the same. Where is that it's much more difficult because of the dynamics, and also because of if you see M87, you can see it like from face up, like, and if you see J star, you're seeing it over all the Milky Way, which also is like kind of looking, and also it's not as active as M87 is. There is not an accretion disk as active as M87. Yeah. So we don't know really, because we are not part of the team. We don't know really how long they will take, but they are really working hard on it. That I didn't know.
So I know another thing that many people have started to think about is adding a space instrument to the EHT network at some point. So we typically don't do radio instruments in space, but you could. And one of the features, advantages you would have for this particular application is you actually would, so EHT relies on having these widely separated telescopes, right, to basically make an Earth-sized telescope. So you imagine if you put one in space, you can make that telescope kind of even bigger, depending upon what orbit you put that other dish in. And also the fact that it moves around in the orbit relatively fast, right? You're not relying on the orbit of the Earth to move it around. You can let the spacecraft move around. That can help you get sort of better time resolution on what's going on with these black holes. So if you're trying to see something like Sag A star where things are changing rapidly, having a rapidly moving around orbital dish that you're doing your data with could help a lot. So that's something maybe in the future we may have an orbital EHT station. I
have a final question just to close up because we're going a little over time here, but sure. It's a nice question. How long is a single event of black hole merging? In time. How long does it take? And this is a question from Avinash over Facebook.
Okay, great question. So basically, it kind of depends upon when you start. So what happens is you end up with a pair of black holes and they're orbiting one another. And if it weren't for Einstein telling us about general relativity, they would just orbit one another forever. But actually, what Einstein showed us is that you get a little bit of energy that's taken away in these gravitational waves, and that energy has to come from somewhere. And where it comes from is the orbit of the black hole. So they fall towards one another. And after they've fallen towards one another, well, then they actually emit gravitational waves stronger because they're moving more quickly and they've gotten closer. And that becomes this sort of runaway process where, the closer they get, the more gravitational waves they emit. So they get even closer. So they emit even faster. So they get even closer. And it's this runaway process. So it takes, depending upon, when they initially got into that orbit, it could take millions of years or tens of millions of years. But as far as our detectors, we're only going to see the last little bit of that. So like the LIGO detectors are typically seeing, a fraction of a second. For some of the lighter objects, they maybe see, tens of seconds of the merger. So it's the last few orbits of these black holes, which is, the numbers are kind of incredible. They're orbiting one another, at many, many times per second. And yet they weigh 10 times the mass of our sun, and they're going around each other, hundreds of times, hundreds of times in a second, which is just kind of mind-boggling. For the really big black holes like Lisa would look at, we would see them for weeks or maybe months, the last weeks or months before they merged with one another. But we'd see other kinds of systems like binaries of white dwarfs that basically take hundreds of thousands of years to merge, and so for us they would just be constant little gravitational wave beacons that would be up there all the time. So kind of depends on the system.
Excellent. I'm sorry, but there is one little kid from Brazil, 7-year-old, who wants to know, and this is really the last question, if black holes can eat space-time. And this is from, I believe, Veronica's child.
Can they eat space-time?
Yeah.
Yeah. Well, I guess in a way, when you have a black hole merging with another black hole, that's sort of like a black hole eating space-time, right? And so what you get is an even bigger black hole. One of the fun things to look at, and I would encourage people to go look at the LIGO site. They have a lot of nice outreach as well. Is for any little kid that's learning their math, they will publish for each of their events how big was each of the black holes, what was their mass, and then what was the black hole that resulted when you put them together. And if you go and you do the math, you see that you're always missing a little bit. And it's the little bit you're missing is the part that came out in gravitational waves. So for like the first one, it's something like 60 solar masses of black hole, but there was like 65 solar masses that went in and only 62 solar masses that came out. So those 3 solar masses were missing, and those came out in gravitational waves. And if you equals mc squared, this famous theory from Einstein, well, that's energy compared to mass. So in that event, they converted 3 times the mass of our sun times the speed of light squared, into pure gravitational wave energy. So these gravitational wave events, despite the fact their amplitude's really small, it's hard to detect them. The energy is incredible. They're the most energetic events in the universe by far since the Big Bang. Much more energetic than a supernova or a gamma ray burst. So yeah, definitely. Thanks for those questions.
Excellent. Thank you very much, Ira. If you need some more answers to this kind of questions, please follow NASA and ALMA on their social networks. You can ask there, and there are people behind those social networks really eager to answer that kind of questions. So I really think it's a good idea. And thank you everybody to follow us today. I don't know if you want to say goodbye, Ira, and say something else.
No, there's been a lot of fun chatting with everybody. I hope everyone enjoyed it.
Excellent.
Happy Black Hole Week.
Happy.
Okay.
Have a nice day.
Bye.
Goodbye.